Okay, our next problem. All right, this is in our series of finding extreme values, all right, analytical methods. What we're doing is we're trying to use endpoints and critical points to identify where possible extreme values would occur. That means max and mins, okay? And as you just saw in the previous problem, or if you've been watching all these, or if this is your first one, calculus can help us define these. And once again, when we're given a problem, we're asked to find where these absolute or extreme values can occur or where they do occur. What we're going to do is we're going to identify the critical points and endpoints. Well, first off, when we look at this problem, we try to identify, is there any endpoints? All right, well, this does not have an interval, and there's no closed interval, so there is none, all right, to identify. So in this particular problem, there is no endpoints. So this next thing is we're going to look at our interior points or critical points. Okay, now critical points, once again, all right, if we wrote this down, is when f prime equals 0 or and, all right, or and or, let's change it up, or and or, where f prime does not exist. Now, so for this one, we're going to find out what this derivative is, okay? And when we go right here, we're going to have f prime. I'm going to set this, change this up. Probably want to maybe change what y is going to equal. I'm going to make this a little smaller, so if you wrote this down, all right, we're going to change this as y, a different color, y equals, it's going to be 1 minus x squared, that to the negative 1/3 power. Okay? Now, from here, we're going to find out what these critical points are. So I'm going to find the derivative, f prime, do negative 1/3. All right, 1 minus x squared to the negative 4/3 power. And we're going to subtract 1. And negative 1/3 minus 1 is negative 4/3. And now we multiply this chain rule by multiplying the inside, so it'll be negative 2x. And write that. Now I'm going to simplify this. And what we have then is going to be negative, negative, positive. So we have 2x, which is on the numerator, times 3. And then we'll have this quantity, 1 minus x squared, the 4/3 power in the denominator. Okay, so we'll look now at our critical points. So where does f prime equal 0, if anywhere? Well, we look at that and we notice that we look at our numerator and set that equal to 0, and our numerator is located right there. So we're going to take 2x equal to 0, and we notice that when x equals 0, that appears to be a critical value. So I know that right here, when I plug that back in to find the actual value at 0, I plug it into the original function. And actually, I shouldn't use f, all right, in this case, because we don't have f. I apologize for that. Confused you. All right, probably didn't confuse you. You didn't even notice. All right, but this actually should be y. I always want to call it by what its actual name is, so y prime. So y of 0, caught myself there. Y of 0 is going to equal, it appears when you plug in that value in, is going to equal 1 over 1, which is 1. Okay, so we have a critical value at 1. The other values, when we take this, are when y prime doesn't exist. All right, so when y prime does not exist, and that is when, if we have a denominator, it's when the denominator equals 0. So we'll take 3, and we have 1 minus x squared, 4/3. And so that equals 0, we notice that it's going to be when x equals plus and minus 1. Now, you take this and plug it back in. Now, if you notice in the original problem, all right, this problem has a denominator, and actually there are vertical asymptotes, okay? Vertical asymptotes that occur on this problem at x equaling positive and negative 1. So these are also where the derivative also won't exist, because in the original problem, all right, it doesn't exist as well. So there are no defined values here, so we won't consider these, all right, as any of our possible max or mins. Okay? So now, what is this value? Is it a max or is it a min? Well, this is where we can, we're going to learn about how to do this more analytically later on. But for right now, we can go to our calculator, and if you punch this equation in, all right, and you punch it in like that, so you have to pause it. You can look at that one, but I punched it in like so, and I graph it. And you can see from this graph, make this up a little higher, is that indeed we do have a minimum value, all right, and this is going to be a relative min, all right, a relative minimum value at this critical point, all right? Y equaling 0 equaling 1. All the other values, all right, there are no minimum maxes, all right? We have asymptotes, which occur right here, which we knew about. And these values do keep on going down, just so you know. All right, and these keep on going up. All right, but that is what we have. So we only have one relative min, and that's at 0. Okay. Hopefully this helped you out. All right, another example. We're going to be another series. So if you want to pause this, all right, copy it down. But once again, how do you solve these? Find the extreme values. You test the endpoints and the critical points. Endpoints, critical points. All right. Once you find them, you plug them in to find the actual relative min and maxes. All right. Determine if they are actually real zeros, because in this case they were not. All right. So we can cross those out because they didn't apply. They were vertical asymptotes from our original function. Okay, right there. And then you can go on your graph, okay, or your calculator and determine those other values, okay, to see where they actually do occur and what type they are, all right, whether they're relative min or max or anything. And that's how we go about finding extreme values for right now.